Hello everyone and welcome to your exciting journey into the world of assembly programming. Today marks the start of course that will expand your knowledge of computer science and programming to new levels. First, I want to assure you that even through assembly languages may seem difficult at first. It opens the door to a much deeper understanding of computers. It's like learning the native languages of digital devices give you clear insight into how they work behind the scenes. As we begin, let's talk about what you can expect. Your main goal is to help you learn how to read and write assembly code. Imagine being able to improve programs for speed or size like a true expert. Creating commands that make your device work exactly as you want, which very tight extra effort. We will start with the basic and by the end you will have the skills to handle high performance applications and even work with embedded system where efficiency is key. You might ask why whose assembly? In the world full of high-level languages like Python or Java, why the low-level patch? Assembly gives you complete control over the hardware, something that's high-level languages hide from you. Whatever you plan to develop performance, critical applications, build security features, or simply want to boost your skills and stand out in the teach industry. Assembly programming is a powerful tool. In this course, we will cover everything from the history of assembly programming to its modern day uses. This course is designed to be interactive and practical. We will work on the hands-on exercise, solve the challenging puzzles, and even take on some fun optimization that will make your mind work in new ways. So, get ready and let's explore how computers really work. I promise this journey will be rewarding. Perhaps even as surprising finding of out of the computer sometimes takes a nap. A wave is only need a quick refresh. Let's start the learning adventure together. Okay. History of assembly languages. Let's explore what assembly languages it's all about. Imagine having conversations with your computer. It's not like talking with a friend using a natural languages full of nuances. Computers are logical and only understand their own simple languages. A set of on-off signals called machine code. But writing directly in machine code is very hard for humans. Imagine trying to remember long sequences of zeros and ones to do a simple task. These were assembly languages helped by acting as a bridge. It provides a human-friendly versions of machine code with cleaner commands like move, add, and jump. This change from complex binary to simple words lets programmers communicate with the CPU more naturally. Assembly languages is designed for specific types of computers. Why do that mean? Each processor, whatever is comes from Intel x86 family, ARM or another type. This of set of commands assembly languages can different from the one computer to another. This lets programmers control and optimize programs for particular hardware, a level of detail that high-level languages usually hide. Think of it like this. If high-level programming languages are like composing a symphony with a full orchestra, the assembly is playing a solo instrument. Which assembly you control every note and every pause, expressing into ideas with precision. That dedicated control is very important in areas where performance and resource management matter, such as in embedded system, device, drivers, and real-time applications. Learning assembly is similar to a chef making bread from scratch. It may take more effort than using ready-made dough, but it gives you a deep understanding of the ingredients and the process. So let's embrace assembly not just a tool, but as path to mastering the art of programming. Get ready to become fluent in these unique and powerful languages. Let's explore the history assembly programming. A story that reflects how computers have evolved in the amazing 94 assembly languages were created to solve the hard task of writing programs in pure machine code. Imagine trying to write a whole book using only ones and zeros. Assemblers were breakthrough because they made programming easier, especially which early computers were programmed by flipping switches of typing binary commands. Moving on the 1960s and 1970s, a time of great space explorations and science fiction progress. Assemblers played a key role. They helped build mainframes and mini computers that powered business and research. You can almost hear the old beeps from those machines. These computers need the efficiency that only low-level assembly could provide. Now, let's step into level in 98. When computers shrunk from huge room sized machines to device you could keep on your desk, like moving from a king-sized bit to a twin. This change sparked the personal computing boom, and assemblers become essential not only in business but also in exciting fields like video games. Assembly languages was used to squeeze every bit of performance from limited hardware. Think of the classic graphics in space invaders. Today, even though high-level languages are popular, assembly still holds its space place. It remains to go to languages for critical system software, embedded programming, and areas where speed and careful memory management are vital. That is the story of assembly. Languages, as old of computing itself, like a wise grandparent in the world of programming. It continues to evolve and attracts those who want to see how computer really work behind the science. Let's celebrate this fascinating history with the excitement of discovering a forgotten family album. Understanding computer architectures. Understanding computer architectures is asking to knowing in the working of a city. Just a city has critical components. Stuck at the government body, reads and infrastructures a computer system has its own central components that dedicate how it functions. Let's dissect these core elements to aperitif, how they come together to power every digital experience. At the heart of the computer architecture, let's the central processing unit, or CPU. It's the brain of the computer, performing calculations and executing instructions that drive operations. Picture it like a maestro leading an orchestra, coordinating every element of the system of products harmonious functionality. The CPU compares the control unit arithmetics, logic unit, and various registers, each playing unequal roles in processing instructions and data. Now, consider memory. In this analogy, uh, memory can be thought of as the short-term memory of your digital ecosystem. Temporarily holding data and instructions the CPU is currently processing. Like a transit warehouse where items are held temporarily before being shipped to their final destinations. Memory ensures that data readily available for the processor to access and use quickly, significantly speeding up operations. Next on your architectural tour is the input-output or EO devices, which acts the continuous connections the computer to the external world. These devices, from your trusted keyboard to complex sensors in autonomous vehicles, allow the computers to receive inputs and send outputs, making interactions with the environment possible. It's as if they were supply lines and customers in your city analogy, bringing in necessary materials and distributing outputs and needs. Finally, we have the system bus. Imagine is the transportation's network connections, every component. A series of highway and roads facilitating the movement of data between the CPU, memory and EO devices. It ensures that all parts of the system and communicate efficiently, much like ensuring goods and service can flow smoothly through a city. Together, these aspects shape the framework of computer architectures, an invisible mesh of interactions that bring your device to life. Understanding these computers offers a prompt applications for how computers perform complex tasks with such processions and efficiency. Just understanding a city layout can provide insights into its culture and functionality. Grapes in computer architectures reveals the interactions and compatibilities of modern computing systems. So, as you explore assembly languages, remember, you are not just programming, you are become an architect of the digital world. Introduction to machines code. The binary alphabets of program, machines code basics, binary instructions, operations codes, opcode, and operands. Machines codes might be dressed to kill, but it's actually the base layer of everything digital, the primal language of computers. Born to rule, or at last rule or your computer's machines codes in an impressive feat of simplicity charged with considerable power. Let's unravel these enigmatic languages and understanding these significations. Machines codes compiles binary instructions, sequences 0 and 1s. They were building blocks of computing. To put in culinary terms, while a fully assembled computer programming might be a complex dash, machines code is asking to the rough ingredients, essentials, basic jet fundamental. This simplicity is defective. The strings of binary digits translate directly into actions executed by the computer hardware. Consider a piece of machine's code as a musical sheets composed of operations codes and operands. The operations code or opcode is the musicane instructions that indicates the actions to perform. Think of is a musical note directions as specifically tasks like adding numbers or moving data. This code is concise and direct to CPU's actions. Next, we have the operands, the data pointers. They like lyrics, that dedicate to what data is being manipulated or sung in this symphony. Operants specify what of whom actions will target. Whatever it's writing data to memory or directions, it's through a specific register. All-round writing and understanding machine's code correctly demands precision and intimate familiarity with the CPU architectures. It reveals the interactiveness of how tasks are processed at the hardware level. These binary communications make upper minimalistic, but its efficiency and direct influence of performance make indispensable. Why machine code? The ability to translate high-level programs down this external level values a program into an elite cycle of computing mastery. I might not be human, reliable at a glance without some heavy head scratching, but is the heartable orchestrating the composites of modern technology. So, as you delve deeper into assembly languages in this course, remember that machine's code, in all its obligating silence and simplicity, it's ever-present just beneath the surface, a binary bullet tearing the potential of ideas into digital reality. Whatever you are querying up code for the next Mars rover of programming something and as minimal on of its drones. Cappuccino machines code lets to instruct with the cures of the machines is not just languages. It's so full of computing living in ones and zeros. Now, who's ready for a binary tango? Components of a CPU, introductions to a CPU architectures, arithmetic logic unit, ALU control unit, and registers. Let's take a closer look at the parts inside a CPU, which is in the heart of every computer. You can think of the CPU as a skeleton orchestra conductor, making sure all parts of the computer work together in harmony. The first important parts in the arithmetic logic unit, ALU. You can imagine it's a calculator. It performs match operations like additions and subtractions, as well as logical operations such as AND, OR, and NOT. The ALU helps the CPU quickly solve complex calculations. Next, we have the control unit, CU. Think of it as a director of a big performance controlling the flow of data in the computer. It reads instructions from the program and tells other parts what to do. If you ever wonder how different parts of a program work together at the right time. The CU is responsible for that. It works like a brain nervous system, sending signals to make this happen. Finally, there are registers. There's a small memory space inside the CPU that stores temporary data. You can imagine them as quickly access notepads, where the CPU writes and reads important information while performing tasks. Registers are used for string temporary results, memory address, and instructions. Understanding how register works is important for assembly programming because it's helping improve the efficiency of a program. Each part of the CPU has a unique and essential role. Together, they form the foundations of how a computer runs smoothly. In assembly programming, knowing how these components work allows programmers to control the hardware more efficiently, making programs faster and better at managing resources. So, if you want to master assembly languages, you need to understand how the ALU, CU, and register work together. How assembly into programming? Now, let's talk about how assembly languages fits into programming. Imagine a pyramid where assembly is the middle between high-level languages like Python or Java and machines code, which is the languages computers understanding directly. Assembly acts a bridge instead of writing long sequences of ones and zeros. We can use text commands to tell the hardware what to do. This district communications with hardware has big advantages. First, assembly gives programmers precise control over computer components. That's why it's important for embedded systems. Small devices like microwaves or GPS systems that need efficiency and exact instructions. Assembly is also used when speed and efficiency matter the most. For example, game developers sometimes use assembly to make sure their games run at perfect 60 frames per second, without wasting any processing power. Even though most programmers don't use assembly every day, learning it helps them understand how computers really work. It's like a car mechanics taking apart an engine to learn how all the parts work together. By studying assembly, programmers can see how high-level code turns into low-level machines operations. Why assembly won't be used to build a modern mobile app? It plays an important role in programming. It's like a special tools in a craftsman's workshop, perfect for optimization skills and understanding of the deeper working of computer systems. It reminds you all the complexity of modern software. There is a simple and elegant structure running everything. Next. Overview is assembly tools. NASM, MASM, GAS, FASM, and TASM. All right. Let's talk about with the assemblers the essential tools that will help you in your journey with assembly languages. Assembler works like translators. They take your assembly instructions and cover into machine's code that computer can understand and execute. MASM, Neat-White Assembler. NASM is one of the most popular assemblers because it's simple, flexible, and works on multiple platforms. Think if a reliable, multi-skilled friend who can adapt to different environments, which is. If you want universal assembler that works well across different systems, NASM is a great choice. MAS, Microsoft Macro Assembler. MAS is designed for Windows programming and works perfectly with tools like Visual Studio. If you are developing assembly programs specifically for Windows, MAS is two strong options. It's like a powerful tool that fits perfectly into Microsoft ecosystem. GAS, GNU Assembler. For Linux users, GAS is a popular choice. It's part of the GNU toolchain and is supported by an active community. GAS is well documented and works on different architectures, making it a strong and versatile options for those working in open source environments. FASM. Flat assembler. FASM is fast and efficiency. It's translated assembly code quickly because it's use a single pass completions method. is optimized for performance and work best with a flat memory mode, making it a great choice for programmers who want speed and efficiency. TASM, Turbo Assembler. TASM is an older assembler that was once very popular. It's not widely used today. It's still found in legacy systems and is beginner friendly, making it a useful tool for learning the basic of assembly languages. Choosing the right assembler. Picking the right assembler is like choosing the right tool for the job. If you need cross-platform support with NASM, if you're working on Windows, MASM is the best choice. GAS is great for Linux users, while FASM is perfect for those who want speed and efficiency. Even TASM has its place for those working with older systems. No matter which one you choose, learning assembler's work will make you a better assembly programmer and help you understand how computer execute code at the lowest level. Assembly languages syntax. Let's embark on a journey into the prices, albeit in guarding world of assembly languages syntax. Pictures assembly languages as delicate sculptured begin crafted. Every chiseled mark here must be diligent for the final outcome. As which any good narrative, labels act as treats. Labels are essentially names that programmers assign to memory locations, like character names guiding a story. They ensure that your journey through assembly isn't bewildering straddle with naked memory address everywhere. Next, let's welcome your trusted partners, the mnemonics. Just like acronyms, help you remember long names. Mnemonics are short, easily remembered words responding machines instructions. Think of them as assembly shorthand instead for registering an alphabet soup of machine's code. Mnemonics enigmatically captures operations like move for moving data, add for adding numbers, and sub for good all subtractions. Now, on the note, children games operands. These all are the workers crying for operations. Actions as lower ADS for mnemonics. Operands can range from register for specific data values. For instance, using an operand remembers selections of weapon. You have the consider which one is better for the task. And let's not forget the using heroes of assembly that try not easily. Comments. Understand them as your sex, whispering wisdom and clarifications into your code labyrinth. Not executable text denoted most elements. Remember, the syntax of assembly is languages and structures, which at architectures preceding is dialect, saying proficient and in fundamental elements acquires for this universal dance. Mastering assembly syntax resembles mastering the grammar of any languages. Imbalance labels, hold mnemonics dear, respect operands, and invite comments. Warmly together, they all unfold the mastery of assembly code creations. Basic instructions set for assembly instructions. As dive deeper into assembly languages programming, we need to get familiar with the basic instruction set. The essential commands that allow you to control the computer. Just like learning the alphabet is necessary for reading and writing, understanding the instructions is key writing effective assembly code. Move, the data mover. The move instructions is one of the most important. It moves data from one place to another, like a waiter transferring a plate from the counter to table. Without move, we wouldn't be able to transfer values inside your program. Add and sub. The match duo. The add instructions adds numbers together, just like putting musical notes together to create a melody. But where there's additions, subtractions follows. The subs instructions subtract on the number from another. You can think of add and sub as pair that always work together in calculations. Next is mul and div. Manipulation and divisions. The mul instructions multiplies numbers while div divides them, giving both a quotient and a reminder. These two instructions like a toolbox for complex calculations, allowing use to work with longer numbers and perform advanced match operations. The jump command. Jump start for jump and allows the program to skip to another parts of the code. It's like playing hopscotch, jumping from one point to another without following the usual path. This makes programs more flexibly and efficient. The cooperator CMP. CMP compare checks two values and sets flags based on the results. The flags helps make decisions in the program. CMP works closely with conditional jumps, allowing the program to choose different actions depending on the comprise results. Why does instructions matter? The basic instructions from the foundation of assembly programming, mastering them will help you write more complex code and understanding how the computer process commands and low level. Just like every great shorty begins with simple words, every great assembly program starts with the fundamental instructions. Data movement instructions. Let's take a closer look at one of the most important concepts in assembly languages, data movement instructions. You can think of these instructions of the logistic team of your program, making sure data is delivered the right place at the right time and the right from. Move, the essential transporter. At the heart of data movement is move, the key instructions responsible for transferring data from source to a destinations. Imagine using hawk speeds to pick up a piece of sushi from one plate register and place is another plate, a different register of memory. It's simple and direct, but also one of the most powerful commands is assembly languages. Push and pop, stack managers. Next, we have push and pop, a dynamic pair that helps you manage the stacks. A special memory structure following the last in, first out (LEFO) principle. Push place data onto the stack, like stacking bricks on top of another, while pop retrieves them, like carefully removing books from a pile while knocking them over. The stacks is crucial for functions, calls, and local variable management, keeping everything organized and efficiency. Load and store, memory handles. Load and store are a responsibility for moving data between memory and register. Load pulls data from memory into a register, like opening a treasure chest to revive valuables. Store, on other hand, move data back into memory, like putting away clutters in clothes for later use. These instructions help manage dynamic data exchange and keep this flowing smoothly in your program. XCHG, the sweeper, is in instructions designer for swapping the values of two operands. Whatever you need to exchange data between registers of temporary hold a value for calculations. It's a useful tool that allows quick and efficiency data swaps. LEA, the address calculator. Load effectivity address. Doesn't exactly move data, but it helps with address calculations and pointer arithmetics. Think of it as a turbocharged calculator that prepares data addresses efficiently, optimizing how register interact with memory. The power of data movement. Mastering the instructions is key understanding how assembly program functions. Together, they create a well-coordinated system that moves, stores, and processes data efficiently. Like financially tuned machine powering your programs. Arithmetic instructions. Performing calculations is assembly. Get ready because we are about to explore the arithmetic instructions in assembly languages. These instructions are the hidden heroes behind countless calculations working non-stop to perform match operations in your programs. Add and sub, the basic match duo. At the front is add, which the responsibility for adding values together. Think of add as smart accurate, carefully swimming up numbers. Whatever is keeping track of scores of a game or manufacturing values in array. Right, next is sub. The opposite of add, sub subtracts one value from another. Just like a budget analytics, cutting down expenses. Together, add and sub give programmers precise central control over numbers, making calculations smooth and efficiently. Mul and div, the manipulations and divisions team. Next, we meet Mul, the multiplications expert. Imagine Mul as a helpful assistant that quickly multiplies numbers and stores the results in the register. It's perfect for scaling up values efficiently. Mul works hand in hand with div. which divides numbers and gives you both the quotient and the remainder. Div is more than just splitting a pizza. It nearly spreaders values make divisions calculations easy to machine. ENC and these decounters. In many programs, you often need to increase or decrease values by one. That's where ENC increment and this decrement come in. They work like the grades in a clock, increasing or decreasing numbers step by step. These instructions are essential for loops, indexing arrays and tracking currents in the program. Why arithmetic extractions matter? Arithmetic instructions may seem simple, but are essential for building complex operations. By mastering these basic commands, programmers and optimize calculations, improve logic, and create efficiency code. So, as you continue your assembly programming journey, use this arithmetic tool visually. They will help you unlock new possibilities and take your coding skills to next level. Logical instructions, performing logic operations in assembly and or XOR, NOT, SKL, SKR. Logical instructions in assembly languages are powerful tools that allow programmers to manipulate data at the bit level with great precision. Understanding the operations is like unlocking a secret layer of computations, enabling efficiency decisions making and data processing with a program. These logical operations are the backbone of bitwise programming, helping developers filter, modify, and compare binary values effortlessly. And the strict gatekeeper. The AND operations is like a security checkpoint. It's only allow a bit to be set if both corresponding bits in the operands are 1. This make is useful for checking conditions. SAC as a verifying is a set of flags meet specific criteria. In programming, AND is often used for bit masking. Allows you to isolate creating bits from the number. Or the open door policy. In contrast, OR is more welcoming. It sets bit if either one or both operands have a 1 in the corresponding positions. OR is grading for combining values, such as memorizing, merging data or setting specific bits without affect others. XOR, the smart comparator. XOR exclusive OR is a bit more strategic. It sets a bit only if one operand has a 1 and the other has a 0. Meaning it highlights the difference between two values. XOR is commonly used for flipping bit states, performing party checks, or even swapping values without using extra storage. NOT, the reverse. The NOT operations is the simplest yet powerful. It flips all bits, turning zeros into ones, and vice versa. NOT is useful for creating negative values in two complement systems for you inventory conditions in a logical operations. The bit shifters, shift left and shift right. are like multiplications and divisions shortcuts. SHL shift bits to left efficiently, multiplying the number by powers of 2. While SHR shift bits to the right, diving the number. These operands are a practicality efficiently when working with binary calculations and optimizing performance in low-level programming. Why logical instructions matter? Mastering logical operations allows programmers to manipulate data efficiently, optimize code, and control program flow at the lowest level. These instructions form the basic of many critical programming techniques. From encryptions and compressions to game development and hardware control. By learning two things is bits, you gain to deeper understanding of the computer process informations, making your assembly programs more powerful and efficient. Comparison instructions, essential for logical decisions making. Understanding the comparison instructions is assembly. Comparison instructions play a critical role in decisions making in assembly programming. They help the program determine how values relate to each other, allowing it to make execute conditional operations. Without these instructions, a program would lack directions, much like a travel without a map. CMP, the judge. The CMP compare instructions acts like a neutral judge, comparing two values. It doesn't change them but sets conditions flags based on the relationships. Whether they are equal, great, or smaller, imagine two verseless facing off. CMP determines which one is stronger, setting the stage for the next move. By reading these conditions flags, the program can decide what to do next, branching, looping, or handling errors, based on the results of comparisons. CMP is a vital tool for optimizing program flow and ensuring that logical conditions are met before executing specific task. Test, the compatibility check. The test instructions work similarly to CMP, but focused on bit-level comparisons. It performs a bitwise AND operations on two values to check whatever specific bits match. Unlike CMP, test does not compare size, but checks for compatibility, making it useful for flags, masking, and bitwise conditions. Think of test, a quickly compatibility check. It silently examines or data without modifying it. If creating bits match, the program can respond accordingly, ensuring smooth executions. Why comparisons instructions matter? Together, CMP and test guide program logic, helping the program decide between different actions. Without them, assembly code would lack control structures like conditional jumps and loops. By mastering these instructions, you'll gain ability to negative complex decisions making process, ensuring that your programs follows the correct path. Like a compass guiding a ship, comparisons instructions help steer your assembly code in the right directions, making the essential tools for writing efficiently and logical programs. Okay. Next, control flow instructions. Understanding control flow instructions in assembly. Control flow instructions guide the program's execution, deciding when and where the next instructions will run. Without them, a program would execute in a straight line. Control flow instructions guide the program executions, locking the ability to make decisions, repath stacks, or jumps between functions. These instructions act as navigators of assembly, allowing programmers to control the logic and structure of the dir code. Jump. The undictional jumper. At the center of a control flow is jump. And instructions that moves executions at different parts of the program without any conditions. Think of jumps as a teleportation tool. It instantly takes the program to a nav locations. This ability makes jump essential for loops, branching and complex logic structures. Calls read, the functions controllers. The calls and read instructions would work together to manage functions and procedures in assembly. Call is jumps a function or subroutine, just like stepping into a side quest in a game of a chapter in a book. When the function completes return, takes the program back to where if left off, ensuring a smooth continuation of executions. And these instructions add modularity, making code easier to manage and resolve. Conditional jumps, smart decision making. Not all jumps happen freely. Sometimes executions needs to depend on creation conditions. Instructions like JZ jump if zero and JNZ jump if not zero decide whether to move based on flags set previous operations. Imagine a decision-making process. Jumps in if a value is zero, like skipping if steps there's nothing left to count. JNZ jumps if the value is not zero, ensuring loops continue until the right conditions is met. Other conditional jumps like JL jump if less, and JG actually jump if greater, allow comparisons between values, helping the program make a logical choice. These instructions enable complex flow control, allowing for else logic and branching structures. Loop. The repeater. Repetition is a key of part of programming, and loop makes this easier by automatically decreasing a counter and repeating instructions until the count reaches zero. It's like a timer ticking down, ensuring the task is complete a specific number of times before moving on. Why control flow instructions matter? Mastering control flow instructions is essential for writing efficient and structured assembly program. These commands allow decision making, looping, and functional calls, making assembly more powerful and flexibility. By learning how the jump, loop, and call functions, you gain control over how a program flows, turning simple instructions into complex dynamic execution paths. Okay. Next is the building a simple calculator in assembly. Let's explore a fun and practical example, creating a simple calculator using assembly languages. This project will help you understand key assembly instructions while showing how mathematical operations work at the lowest level programming. Additions using the added instructions will start with addition. Basic operations we learn in early March classes. In assembly, we use the add instructions to sum of two numbers. Think of like a bank teller adding money to your account. Simple but important task handled by the arithmetic logic unit, ALO. Subtractions using the sub instructions. The next is subtractions, performed using the sub instructions. It allows use to find the difference between two values. Imagine computing quantities and subtract the ones you promised to your friends in programming subtractions. It also use it in error corrections and balancing calculations. Manipulations using the mul instructions. For multiplications, we use the mul instructions. Think of a baker multiplying ingredients to make a bigger cake. In programming, multiplications is crucial for scaling values and optimizing algorithms. Making it essential tool for many tasks. Divisions using the div instructions. Finally, divisions is done with the div instructions, which splits a value into a quotient and a remainder. Imagine sharing a pie among friends. You need to divide it precisely so everyone gets so far share. These operations is vital for calculations involving fractions and rescue distributions. Why this example matters? Each arithmetic instructions in your simple calculator demonstrate how its match translated into code. By understanding these operations, you build a strong foundations into assembly programming. Grab your keyboard and start experimenting with numbers. These hands-on example will sharpen your logic and programming skills, while giving you clear look at how assembly handles calculations. Next, register and their usage. Understanding CPU register in assembly. Register are like the CPU memory shortcuts, helping in process data quickly and efficiently. Just as synapses in the brain allow for fast communication, register store and transfer data inside the processor, ensuring smooth executions of tasks. General Purpose Register, GPRS. Handle to many tasks such as arithmetics, logic operations, and data movement. Think of them as a set of tools in a Craftsman toolbox, ready to tackle different challenge. In x86 architectures, the most common GPRS are AX, BX, CX, and DX, used for calculations and strong temporality values. Segmentic registers, memory managers. Segmenting registers help organize memory into different sections, making it easier for the CPU to manage data. Each register has a specific role. CS, code segments, holds the program instructions. DS, data segments, stores data used by the program. SS, stack segments, manage the program stacks. This register keep memory organized, allowing the CPU to switch between tasks efficiently. Pointer and index registers. Data navigators. Pointer and index registers help to locate and move data inside memory, similar to a GPS system guiding a road. Small k register include SE, source index, and DE, destinations index. Move data between memory locations. BP, base pointer, tags, functions, parameters, and stacks frames. SP, stack pointer, manages data storage and retrieval in the stacks, ensuring proper execution flow. Instructions pointer, IP. The program guide, the instructions pointer IP, tells the CPU which instructions to execute next. It acts as a traffic director, keeping program executions smooth and continuous. Flag registers. The flag registers keeps track of the CPU status and affects decision making in programs. It set conditions codes based on operations similar to a scoreboard tracking important game statistic. Why register matters? Understanding and using register efficiently improves program speed and performance. Science register operate much faster than regular memory. Optimizing this use helps reduce slowdown and makes program more efficiency. By mastering register usage, you can write faster and more powerful assembly programs, transforming code into a well-optimized machines at precision and speed. Next is stack and memory management. Memory management is an important part of assembly programming, helping the CPU store and organize data efficiently. It involves handling memory structures like the stack and memory segmentations, which ensure smooth programming executions. The stacks, a last in, first out LEFO structure. Think of the stacks a tower of tries snaked on top of each other. It follows last in, first out LEFO rule, meaning the last item added the first on removed stacks is used for. Storing functions parameters, saving returns address, so the program knows where go back after function call, keeping track of vocal variables. At the center of stack manager is stack pointer SP, a special register that always points on the top of stack. It helps control how data is added and removed, making sure everything runs smoothly. Push and pop, managing stack operations. The push and pop instructions handle data movement in the stack. Push add the value to the stack, like taking dishes on the top each other. Pop remove the topmost value, like taking the top dish of the file. These two instructions are critical for function calls, ensuring that values are stored and retrieved properly. Without them, program will lose track important information during executions. Memory segmentations, organizing memory efficiently. Memory segmentations is a method of dividing memory into sections, making it easier to manage. Each section has a specific purpose. Code segments, CS, store program instructions. Data segments, DS, holds variables and constants. Stack segments manage the stack's operations. Think of segmentations as separating different tasks into dedicated workspace, ensuring what code, data, and stack operations don't interfere with each other. Calling conventions. Framework for function calls. Calling conventions are rules that define how functions retrieve arguments, return values, and manage the stack. They ensure that functions communicate properly and prevent errors in program executions. Think of them as different way people following equated at a formal event. Each with its own rules, but aiming for smooth and efficiency interactions. CD, SCL, the color cleans up. The C declarations conversions makes the color responsibility for cleaning up the stacks after a function call. This gives flexibility, allowing functions to accept a variable numbers of arguments. It's widely used in C programs and assembly routines because it supports dynamic functions calls. But it also requires more stack management from the caller. std call. The caller handles cleanup. Which standard called the called functions caller is responsibility for cleaning up the stack. This makes functions calls simple for the caller. As there's no need to remove arguments manually, it's commonly used in Windows API functions, ensuring and structured and efficient calling systems. Fast call. Using registers for speed. Fast call improves performance by passing arguments through CPU register instead of placing them on the stack. This reduces overhead and makes functions call faster, especially in performance critical applications. It's deal for speed sensitive tasks where efficiency matters. Discal, specialty for C++, number functions. This call is used specifically in C++ for calling members functions. It's automatically bases this pointer of the functions, allowing into access of object-specific data. This convention ensures the class methods handle data properly, make in essentials object-oriented programming in assembly. Why calling conventions matter? Understanding calling conventions is important for ensuring compatibility between different functions, optimizing performance, and managing the stack efficiency. Choosing the right conventions help programs route smoothly and supports cross languages communications in assembly. Practical exercise, stacks operations. Um, Hands-on stack operations exercise in assembly. This exercise is a great way to strengthen your understanding of stack operations, a key concept in assembly programming. Think of the stack as a dynamic storage system, where data is temporarily stored and retrieved as needed. By practicing with the stack, you will gain confidence and managing function calls, parameters, and local variables. Handling parameters which push and pop. Imagine the stacks as an organized assistant. Carefully strong functions parameters. Push. Add values onto the stack, like safely storing important documents for later use. Pop retrieves tools values when needed, like taking out documents for review. Using pass and pop. You can pass and retrieve function parameters efficiently, ensuring smooth executions. Working with local variables. Local variables exist only while a function is running, making the stack an ideal place to store them. Think of the stacks as a shared workspace where each function temporarily reserves space for these calculations. This method is efficient because it's always data used when needed and discarded when no longer required. Using stacks for local variables ensures better memory management and keeps programs running efficiently. Next, managing return address with call and read. When a function is called, the return address, the place where executions should continue after the function ends, is stored on the stack. Call place this return address on the stack, like marking your path on a map before exploring a new router. Read retrieves the return address and takes the program back to where it left off, ensuring smooth executions. This system keeps track of functions call, preventing errors and helping the program returns to the right locations. Nested functions and stack growth. Calling functions inside their other functions, nested functions, adds more layers to the stack. Imagine a roller coaster which loops. Each function calls an NF loop, intercasing them. The stack grows and shrinks dynamically, managing multiple functions called without confusions. By practicing needs functions calls, you'll learn how the stack adjusts and manage depth, making your programs more efficiently. What this exercise matters. By engaging with this practical exercise, you'll develop strong stack management skills. Understanding how push, pop, call, and read work together will help you write better, more efficiently assembly programs. So explore, and refine your skills. Each steps brings you closer to mastering stack operations in assembly programming. Okay. Subroutine and functions. All right, folks. Welcome to the part of your adventure into assembly where functions and subroutines come into play. You see in assembly code, like in your everyday lives, breaking down tasks into smaller, manageable pieces makes everything so much easier. Imagine you've got a morning routine that involves making coffee. Each step, boiling water, grinding the beans, and so on, is part of larger routine. Similarly, in programming, subroutines allows use to break down a programming into bite-sized chunks. In assembly subroutines, we basically snippet of code you want to resume multiple times through the program. Um, think of them as your go-to coffee recipe that you will pass it down generations. Essentially, using subroutines is the computer's way of following grandma's recipes without needing to call her every morning. It adds efficiency and elegance to your program. Subroutines are invoked using instructions like call when a call instruction is executed. The computer essentially bookmarks where it was, jump to the code of the subroutine, excuses it, and then returns to tag a bookmark with red. It's like a teleportation trip to a coffee shop, shipping your breath and immediately returning home without ever touching the ground. Moreover, these subroutines are known as functions when they operate with parameters, making them even more versatile. Functions return control to be main part of the program after executing selected code blocks. This structured and modular approach is vital, uh, especially in larger programs where debugging or updating code becomes easier because of this handy subroutines. Keep in mind that while we live in the power of modular code today, some caution is needed. With great power often comes great debugging responsibilities. As exciting as it sounds to have subroutine after subroutine, keeping track of what can become a bit like managing a library of secrets, coffee recipes. Label appropriately and comment liberally. In the world of programming, clear code achieves harmony, interrupts and expectations, handling interrupts in assembly. All right, let's delve into fascinating world of interrupts and their close continuous expectations. Imagine you are in the middle of an intense online game fight. Suddenly, your gaming console receives a notification that someone knocking at your door. You are faced with decisions. Pause the game and attend to the door, or completely ignore. In terms on computers, this is a bit like receiving an interrupt. Interrupts are akin to an target knock on a CPU doors, demanding its immediate attention to an event outside its current task list. They are like that friend who always seeks attentions in the most inconvenient times. Necessary that occasionally disrupting. They are triggered by events such as inputs from the keyboard or mouse, signaling the processors monetarily halt its current trial and focus on something more immediate. Expectations, on the other hand, are like a hiccup in the CPU's smooth operations. They happen when something goes wrong interminally. Perhaps divisions by zero or access to a restricted memory area, and require attentions but originated within the CPU itself. To manage the interrupts effectively, we use interrupt service row times, or ESRS. Things of ERS like the unavailable personal assistant. Once the interrupts calls upon the CPU, the ESR ensures that necessary actions are taken to address it, eventually return of the CPU, return CPU to its previous arrangement, much like how going to answer the door doesn't mean your game is over. You just pause it at resume. Understanding, managing, and holding these interrupts efficiently is crucial in maintaining the steady rhythm of operations with the CPU. It ensures that tasks are balanced and rescues are utilized without dropping or misdialing critical information. Just like a well choreographed dance amidst distractions. By handling this reliability, assembly languages becomes an ally in managing at the many phases to processor operations smoothly. Most currently, no one wants their computer to crash or freeze because I didn't know how to handle an unexpected knock. Leverage you knowledge is ESRS as you CPUs. Polite butler to manage these interruptions gracefully. Example, interrupt handling. Let's divide into real magic of interrupts with an example of interrupt handler. The role of an interrupt handler is much like the efficiency juggling of multiple tasks that demand attentions. Imagine you are just a birthday party, hosting guests in a person and virtually. Every time you get a gift, you pause and announce to keep everyone engaged. Well, that's your CPU juggles tasks, attending to the most urgent matter while ensuring all progress is remembered. Firstly, the interrupt handler begins by identifying the interrupt source, determining who or what needs attention. It's like your party host noticing who currently trying to give a birthday gift. This is where the ESR steps into the spotlight. The initial steps is saving the processor state, essentially keeping track of where you left off. Like bookmarking your page in a novel before leaving to grab the door. Next comes executing the appropriate interrupt service runtime. This is when the CPU temporality shifts gears, addressing the NEF task, which could be anything from executing NEF instructions to processing keyboard inputs. Once the event is resolved, the processing of restoring the processor's state comes into play. It's akin to placing mementos of the gift back in the memory, ready for later enjoyment. Finally, the last tip is returning of the main executions, where everything resumes to how it was, like hitting play after a quick pause. These seamless transitions ensure efficiency and prevent jarring disruptions in processing, keeping the CPU stable and maintaining harmony across operations. This journey throughout an interrupt handler also uncovers concepts such as precise versus imprecise interrupts. Think of it as the difference between a planet, a calm surprise and a chaotic one. Priority-based handling ensures that the more crucial task the precedence, ensuring an organized task flow. If two friends try to give you a gift, you'd probably attend to the one holding the cake before and which a card. It's this clever orchestrations and the art of balancing priorities and nested interrupts that ensure any signals or interruptions in addressed with precision. Akin to skilled event planner, handling gateways on a task which is and grace. Managing this efficiently helps prevent anyone on anything from being left in the dust. Is the hallmark of Tawlokov programming against interruptions. Okay. Input, output in assembly. EO operations, types of EO devices and assembly languages instructions. As we went into the domain of input and output in assembly, let's start by understanding and the fundamental role of these operations. Imagine trying to enjoy conversations with your home smart assistant, but it never hears you. Without efficient input and output operations, computers remain Solarity entities cut off from the world they mean to enhance and entertain. When we talk about input output or EO operands in assembly, we look closely at how computers communicated with external peripherals. The operations empower your device to interact, channeling users' commands from input device like keyboards and mice throughout in the instructed pathways of processing. And back to output where they materialize as visual wonderments of on monitors or melodic notes from speakers. In assembly languages, they link which EO involves at tight. Mindful control of communications channels called ports. The in instructions is your way of capturing data from an input port, akin to collection whispered secrets throughout a telephone line, ready to be unfolded. Whereas out is the sending data to an output port, the equivalent of directing a conductor to bring a full orchestra in majestic melody. A key benefit of knowing assembly languages determinant of EO is control over performance and rescue management. Brokering Symfony behind the scenes that produces quality outputs without delay, like reading inputs from a keyboard swiftly and directing beautifully rendered graphics onto the screen. Think of its having LD controls at the sound deck during a concert. Mm, you ensure each instrument plays as optimal volume and pacing of a harmonious results. EO operations, the symbolic flow of data that breathes life into your mechanical creations. They are not just about receiving input and charging output. They are about making sure the digital conversations flow smoothly between the user and machines. Understanding the assembly instructions give you insight into how low-level control allows to hone the efficiency of the exchange and orchestra better overall computing performance. In summary, harnessing the power of I/O within assembly ensures we mating dialogue between CPUs and external device, embodying the delicate dance of interaction of defines modern computing. These clear communications is essential no matter the size or scope of your applications, from basic desktop to complex virtual environments. Next is port mapped EO. Understanding port mapped EO, key operations, and advantages. Let's navigate into the world of port mapped EO, a technique intimately tied to how we interact with device through specific portals. Imagine yourself as diligent postal worker with defined routers and postal codes. Each represents a unique address for the letters a packet that need precision handling. Similarly, port mapped EO using CPU instructions that's communicated directly with individual EO devices through designed port addresses. In the realm of assembly languages, this means challenging instructions like in and out to underlie crucial transmission between the CPU and peripherals. Each EO device opens unique port address serving as assigned postbox where data is received and dispatched. Port mapped EO is asking to ensuring every parcel of data reaches in indeed recipient without deviations. The in instructions draws a parallel to retrieving data awaiting in the port address, while out is command dispatching informations outward, similar to posting that finalized postcard. Such operations enable timeless data flow which coding into structured memory spaces. Think of as trailing messages between components of the larger data train, but efficiency at avoiding misdeveloped messages. There are notable advantages to managing operation in this way.
Direct control over how we communicate with device grants faster processing and operational efficiency. Another bonus is how clearly defined the realms of data storage and device control immediately. That's the value of knowing who gets what's data without getting in lost in translations. It's asking to your postal worker bypassing out traffic and confusing neighbors. Thanks to deadlined map of the delivery layout. Moreover, using exclusive port address means favor plug points. Conversing recurs for each device reflective process while limiting interrupts risk. This highly coordinated interaction with port MAPED EO response what is pivotal. LJagging device communications channels their specific needs while with crystal clarity. Port MAPED EO efficiently merged precisions will which save dimensional data handling. Solve deploying is indispensable role in assembly languages. Shoring insights into how the tiniest circuits collaborated for performance at its finest. SAC perspective, operations deliver seamless connectivity where all devices routes leads to paths teaming with data delivered of point every time. Through for MAPED EO, we lay the groundwork for harmonious interaction with peripherals, turning simplicities, complexities into fluent partnerships between hardware and involving commands. Memory MAPED and EO, MIMO, is a fascinating concept that integrates memory and EO operands into the same address space. This means that EO devices can be controlled and accessed using the same instructions used for memory operations. Why would be bother doing this, you're wondering? Well, let's take a trip into the practical world. Imagine we got a small embedded system, let's say a microcontroller in a washing machine. It doesn't have a plenty of space for EO ports. Yet it needs to control various components such as the water pump, drum rotation motor, and maybe even a Wi-Fi module. What do? Assign each an address in the same space you set by your memory. This way, when the microcontroller sends a command to a specific address, the responding EO components react. It's quiet, like having an universal remote control that works for your TV, sound systems, and air conditioner all from one spot. They all respond based on the frequency you set, which in computing terms are the addresses. The charm lies in the simplicity and efficiency for small systems. Of course, there are drawbacks like potential address, space conflicts, and utilizing valuable address space for EO rather than data storage. However, the trade-off can be worldwide when space is a premium. And that's why MMEO is extensibility used in embedded systems, where optimizations makes the difference, embrace the harmony of shared space, but use in to avoid conflict and mind peace in your digital ecosystem. Next, reading from keyboard. Let's divide into practical world of assembly by reading input from keyboard. It's much more fun than watching paint, I promise. When programming at this low level, you often have to go a menu which the hardware using watch know is interrupt driven I/O. Imagine this. You are writing a letter, typing every word yourself. No autocorrect fire to help. This is similar to programming is assembly. You have direct control over the inputs. To read keyboard inputs, we use a BIOS interrupt. Interrupts are like a tap on the shoulder for your processors, saying, hey, pay attention to this. When you press a key, the keyboard generates an electrical signals, which is interpreted by the computer as an interrupt. Whereas magic happens, your CPU jumps to a function or routine associated with the interrupt. In your case, is the BIOS interrupt. Then line move AH 0x00 prepares the CPU for the keyboard interrupts call. The integer of 0x16 lines does exactly that. It calls the interrupts. Well, it's all done. Poof. Your key press is caught and stored in the all register. And notice there that we used a variable named key to store the results. I can be yourself secret valued where the ever key preset is stored nearly. A lighter word of caution. In real world applications, you will want to handle different events, such a multiple key press, key realizers, etc. But don't worry, by understanding this basic structure, just already halfway there in building responsivity and interactive applications it's in assembly languages. Next is using labels and comments. Imagine trying to find your way in an FCT with a map that has no street names. You probably get lost and go in circles. In assembly programming, labels, the comments work like those missing streets names and landmarks. They help you navigate the code. Labels are like bookmarks in your programs. They mark important points in the code so you can return to them later. If you need to repeat sections to skip ahead, you place of label and reference if jumps or loops. It's like telling your GPS, take me back to granny house because you shaved the location airliner. Comments, on the other hand, are like little notes explain the code. They may seem unnecessary, but when you review program month later, they remind you what each part does. Imagine opening your Friday and mistaking soup for ice cream. Not fun. Similarly, commands improvement in your code. They add context, making complex instructions clear and easy to follow. In your example code, labels like start and loop here act as sync points, showing the program structures. Comments explain actions like setting up a register or looping make the code easier to understand. Even if adding labels and comments feels like extra work now, your future self or whoever reads your code will be grateful. Clear labels and comments are essential tools for smooth code navigations. Assemblers and linkers. Transforming assembly to machine code. Assembler and linkers are essential tools in programming. They convert assembly code into machine languages so the processor can understand. Without them, your code would be useless, like performing Shakespeare at the dog shows, where no one understands a word. The assembler is the first step. It takes your assembly source code and converts into object code, which is not yet ready to run. Think of it like writing a book in English and translating only some chapters into French. The text is partly translated, but it still needs to be full assembled. This is where the linker comes in. The assembler produces separate object files like piece of a puzzle. The linker put everything together, combining these files into final executable program. It also resolves dependence, just like linking two separate stories into a single choice novel. To simplify, think to assemblers and linkers like coding Emil. The source code is the recipe. The assembler grades, integrates, and prepares, then creates object files. The linkers is the chef who assembles the final dish, the executable file. This process of turning assembly code into executable program is both complex and crucial. Just like a conductor leading on orchestra, assemblers like and linkers ensure everything works in harmony. Thanks to the tools, programmers can focus on writing, logic, and solving problems, while the assembler and linker handle the technical details, creating a full functional program. Debugging, practical exercise, writing a simple program. Now we explored assembler and linkers. It's time for exciting part. Writing assembly program, it's like learning to ride a bike. Challenging at first, but rewarding once you get the hang of it. Your task to write a program that points hello world on the screen in the classic beginner's program, and for good reason. In teachers, the basic of data handling, system calls, and executions follow. Step 1. Define two data sections. Before writing instructions, you need to define the data. Think of this preparing ingredients before cooking. The line message db hello world 0. Create is a message variable ending with 0 to mark the end of the text. Step 2. Write the code sections. This is where the actual execution happens. Your playground for logic and operations. You use basic instructions to move data into registers and make system calls. For example, move ADX len, move ADX message. The commands set up the message to be printed system calls like integer 0x18. Act as bridges between your program and the operating system, just like sending the message to the CPU to execute task. Step 3, execute and see the magic. At first, the process may seem complicated, but once you run the program and see hello world appear on the screen, everything will click into place. This is more than just simple program. If you first step into assembly programming, the best way to master is to divide and experiment. So enjoy the challenge and watch your code come to fine. Okay, this is all today. Thank you very much for meeting and see you at the exercise. Thank you so much.